The title for section 8.1 day 1 is logarithms. Now, before we begin the notes, logarithms is a really powerful tool in math, and it's a very interesting subject. It's very, very powerful in doing calculus work. A logarithm combined with doing exponential equations gives a very, very powerful way to solve bigger equations. And if you ever take a calculus-based course, you'd really see what a logarithm is good for in those scenarios. It's also a very powerful tool in chemistry. Even in grade 12 chemistry, if some of you have already finished it, you would have seen the logarithm. You probably didn't understand what it was, but it is, again, a very, very powerful tool. Now, logarithms is an interesting topic. It is not the most hated topic in pre-calculus 30. If we were going to do a vote, it'd probably be chapter 6, trigonometric identities. So logarithms, some people like them, some people don't. But here's where they're really interesting. When we are taking them, very, very few people complain about them. But when we're done, even like 2 weeks after we're done chapter 8, if I would ask anybody, hey, what's a logarithm? People who'd never complained about them were able to do all the work would be like, yeah, I don't really know. They're a really abstract concept. And here's part of the problem. What we are going to do is we're going to learn how to work with them in chapter 8, but we don't actually see their greater purpose. You have to take a calculus-based course to see their greater purpose. And so here's how I'm going to begin, even though this isn't in your textbook. Anytime you're wondering, what is a logarithm? I want you guys to think of this graph. Everything is graphable, and this is going to be another one of your memorize these graphs. It actually is the last one. Okay, this is the last of the long line of memorize all of these different graphs, and it's going to pay dividends. And so in its truest sense, what is a logarithm? It's an inverse. It's an inverse to an exponential function. So let's say we took any exponential function. Okay, and we just finished looking at these. So this could be y equals 7 to the power x, a 2, a 3, even that letter e, which is a very, very important one. Now, what is an inverse? We've taken that very early in this course. An inverse, and there's a number of ways to do it. We've done the hand switch. It is also graphically a flip over the line down the pipe y equals x. So what would it look like if I took this and did a fold, a reflection over that line? It would look something like this. And then you might be like, oh yeah, I've seen this one before. That was one of the first things we drew when we were studying the inverse way back in chapter 1. So here's the idea. If this is an exponential function, its inverse, in red here, we give it a name called a log function. Now, you're going to start to judge it right away. You're going to be like, why do you got to mess it up? Here's how you'd actually write it. And I didn't invent this, so don't kill the messenger. What you do is you put a little subscript 7 there and then an x. If this was a 10, well, then you'd put a little 10 there, and so on. Okay? This is how we would call or name this equation. If this original was y equals 7 to the power x, its inverse is y equals log 7x. So most people just accept it. They're like, well, some mathematician wanted to be all fancy. I got the idea. But now you're going to see us venturing into, not hard, but kind of like, where does this go? And so again, I challenge you to always come back to this graph. So to start with, okay, and this we're just going to do the quick review of the hands. Let's say you had an exponential equation. Okay, so any number like 7 or 2 right here, and then you went to some power equals x. If we do the variable switch, this is what the log equation is. And so it's just basically the backwards version. The c is the 7, and everything else looks the same. And we're going to see really quickly some of these ideas. The first one I'll address is c can never be 1, right there or right there. Because imagine it if you had just a 1 there. 1 to any power is 1. It would not be an exponential function. If you just had y equals 1 to the power x, that's just a flat line at a height of 1. Okay, and so we'll discuss those later on. Now, we jump into the rewrite. And again, you're going to be going, okay, I get it, but you're going to be left wondering, well, how can this possibly be useful? You will see it later on. Okay, again, and you just have to be patient with it. For the rewrite, we are going to learn a very important skill. Okay, and it just goes like this. Let's say you had 2 to the power 3 is 8, and you can't argue. 2 cubed, 2 times 2 times 2 is 8. If you wanted to, you could rewrite this as a log. And it would go log with a little base 2, a normal size 8, and then a normal size 3. And again, you'd be wondering why? Why would you even want to do this? Please be patient. There's a reason. I'll do one more. Let's say you had 3 to the power 4 equals 81. So 3 times 3 times 3 is 81. And you're like, perfect, I got it. If you wanted to write it as a logarithm, you would write the 3 as the base, and 81 is a normal size, and then a 4. I'm sorry about the PDF notes. Sometimes it doesn't quite show this as a subscript or this spot as a normal size number. I lied. I said I'd do just one more, but I'll do another one. You can do it with variables. Let's say you had 2 to the power x is 16. If you were going to rewrite it as a logarithm, it would be 2 as the subscript, 16 normal size equals x. Now, this is where we want to practice up today to do a little bit of work. I'm going to jump over number 4 really quickly. And in number 4, okay, your calculator, if you even just take one quick glance at it, any scientific calculator has this button on it. It's very, very useful. It is designed always to be a base of 10. And that's a very nice number to work with. We know that. That's how the metric system was designed. And just don't worry, we'll use that later on. Now, for number 5, this is where we look at some actual calculations. And I think you guys should be all over it. I got to be able to all over my spelling. So we are going to evaluate. We're going to take a look at what are expressions. Now, if you can glance up and down from the PDF notes, again, this is supposed to be a subscript 2, then a 64. Now, here is how the notes would have been. This would have been the original question. We're just trying to say, what is the value of log 2 64? And again, I remind you, this is very abstract. You might be wondering why or how or like what's going on? Who would even need this? But just watch where this goes. We're trying to say, what would this equal? Because this is basically just a number. So here's a little trick that I learned. Why don't we just say, what does it equal? You can go a question mark, or you could just go a little x. Now here's where I want you guys to watch the rewrite. This is why we were practicing rewriting it, but you can work backwards. And there's a very, very easy way to do it. Don't even look up here and try to think yourself backwards. I want you guys to watch. What we are going to do is we're going to take this 2, and I'm going to swing it around and go 2 to the power x equals 64. So we're going to go 2 to the power x equals 64. Now here's what it essentially becomes. To solve this equation that you see in black here, all we're trying to do to say what is it equal to, we need to know that now, because we rewrote it, we took it backwards from log to exponential. What would x be? Now you could do it like this. I'll just write it up here so it doesn't get too low. We could change both to bases of 2. 64 is 2 to the power 6, and now we have the equality that we learned in chapter 7. 2, well then x must be 6. That's what it is. If you had some fancy calculator that you could type in log 2 64, and any of the bigger calculators like the TIs can do it, and then you hit equals, it would spit out a value of 6. So that is how we're going to finish today. We're just going to do a stream of examples, getting used to that, doing an evaluation. And so our next guy that we're going to evaluate, and I'll try to again write it just like it would be on the board with the proper subscripts. If we had log subscript 3, that's the base, and then a 27, and we were told to evaluate it. So we're going to do that little trick. We're trying to say, what is this equal to? Well, let's just put an x down. And then if you follow, what we're going to do is we're just going to follow a little loop. To take this expression with the equals and the x and rewrite it exponentially, you go 3 to the power x equals 27. So we have 3 to the power x equals 27. And then again, you can either just go right to the answer and say, hey, well, that's a 3. 3 cubed is 27. Or you could do the equalities where you have 3x, 27 is 3 cubed. So 3 and 3, well, then x is 3. And that again is the value. If you would type in just straight out log 3, 27 into a fancy calculator, hit equals, it would spit out an answer of 3. We've evaluated. So hopefully you're not too intimidated. The next guy. Let's say you have log, and no, I'm not forgetting anything, 1,000, and we're supposed to evaluate this. Your calculator, not even a big guy, could handle this with ease. But here's how we want to begin. Okay, we want to say, what is this equal to? So we can put a little x down, and I think you guys should do this once. Right here, when nothing is there, it is assumed to be a 10. It's assumed to be a 10. Just like when you have an x, it's assumed to be a power of 1. This is the logarithmic version of it. You'll get really used to that. And now we can do the little rewrite. We have 10, and if you do the loop, to the power x is equal to 1,000. And then again, you can either get them the same, where you go 10x and 10 to some power, or you could be like, I know what this is. If x is 3, that's what it is. And that's what this solution is if you have just log 1,000. The next guy should be quite rewarding. Letter D, if we had log 7, 1, and we were supposed to evaluate it, well, don't forget the little trick. Just let it equal x, do your little loop. 7 to the power x is equal to 1. And if it's early in the morning, you might be like, I don't know. But if it's anywhere later than the morning, you'd be like, I know what it is. Anything to the power of 0 is equal to 1. That's what x would be. That's what this is equal to. That's what log 7(1) evaluates to. Now, for our remaining examples, we're going to have to work for it a little bit, and our work with radicals from pre-calculus 20 should pay dividends. So let's say you had to evaluate log with the base, the subscript of 2, and then square root of 8. So don't forget your little trick. We'll say it equals x. Do your little loop. 2 to the power x equals root 8. 2 to the power x equals square root of 8. And now, here's where I don't think you can just eyeball it and say what it is. What we need to do is work with it a little bit. Now, first of all, what does a square root mean? A power of a half. 8 is 2 cubed. So we have 2 to the power x equals 2, and then we multiply to be 3 halves, and now we have it. We have our equality. We have the 2's, therefore the exponents must be equal. Our final answer is 3 halves, and then I'm going to do this just a few more times. If you were able to type this expression, log 2 root 8, into your calculator, just that, hit equals, it would spit out 3 over 2. That is what it evaluates to. And before you freak out when you take a scan at letter F in the PDF, if we can just work with our exponents, it is not really that hard. And it's not crazy hard radical work, even if you hated working with radicals in the previous course. So let's say you had log with a base of 9, and then I'm going to have to write this one really neat. This is a fifth root, and that wasn't really neat. It's hard to write small. This is a fifth root of 81, and we're supposed to evaluate what would this equal if you're able to type it into a calculator. So we remember our process. Let it equal x, do your loop around. 9 to the power x is equal to the fifth root of 81. Now, we have to get them the same base. And if you just kind of take a look, like the work in chapter 7, well, this is not going to be too bad. We have a 9. 81 is simply 9 squared. That's 81. What does a fifth root mean? 1/5. And this was not near as hard as maybe what you thought when you first glanced at it. Multiply your powers to 2/5, and we have x is equal to 2/5. We've just evaluated that expression. And we have 2 more to go. Then second last one that we will take a look at. I'll squeeze it in here because this one isn't giant. It might be just intimidating on the surface. We can also have the full thing given, and we can solve these like an equation because we have enough practice even with just 6. Instead of doing the little trick of letting equal x, what if you just dropped into this and somebody said, here's an equation, solve for x. If you use the little loop around and convert this log expression, this log equation, into an exponential one, it's really not bad. So we start with 4, do the loop, to the power -2 is equal to x, and let's just tweak this. A negative exponent means flip, and 1 over 4 squared is 1 over 16, so it wasn't as bad as you think. I know it's taking the next jump away from what we've been doing in the first 6 examples, and then for your final one, let's say again, you, for letter H, had this full expression. Log, base 64, and then an x, and then equals 2/3, and we were supposed to solve for x. So it does take it to the next step. What we would need to do is the rewrite. 64, swing it around to the power 2/3 is equal to x. Now we have to crunch our numbers here, and here's what I would actually do. Break it up. Don't try to do this all at once. That's impossible. I don't think you could argue that 2/3, you could write it as 1/3 and 2. Now, why would I have done that? because I've done enough exponent work to know that 64 to the 1/3, the cube root is 64, is a perfect 4. And then 4 squared isn't too bad to do in my head. It's a 16. Now, to wrap today's lesson up, I just want to remind you guys, you go through all this and you're like, okay, I understand how you got 16, even though I wouldn't have seen this coming. And then somebody says, after 15 minutes, what is a logarithm? Many people would be like, yeah, I don't know what a logarithm is. Here's again what I want to just demand you guys do. Anytime you're thinking, yeah, what is a logarithm? Even though you might be able to do logarithms till the cows come home, remember it's an inverse. It's taking an exponential equation and then it's flicking it over the line down the pipe. This is an exponential graph, that's a log graph. Even though it doesn't help you solve this problem, that is what I want you guys to think about.